All right, everybody. Oh, that is much louder than usual. Welcome back to System Software. How's everybody doing? Good? Yeah, okay. Last semester, everybody would clap at the beginning of class. Oh, you don't have to. That's okay. Anyway, so does anybody have questions from last time about variables, the new LLVM instructions? Who started working on Project 2?
I've already finished Project 2.
Okay. Oh, wow. Oh, you got applause. Okay, so one person. Yeah, I'm sure you'll have questions as we go on. But yeah, anything about last time? Simple tables? Stack variables? Nothing? Yeah.
I mean, we talked about last time, besides the linked list, is there any other implementation that we could use?
Yeah.
Really a search function.
Yeah, so you could, where did I put this? So you could, you can use the linked list. So there's many, so basically the simple table is the dictionary ADT, which I think you learned about abstract data types, right? So the difference between a list and a linked list, you can implement the list ADT with an array, with a dynamic array. There's many ways to implement it. The doubly linked list, singly linked list. So the abstract data type doesn't care about the implementation, just cares about the functional behavior of the methods that you have on that ADT. So for the simple table, it's really just a dictionary, a mapping from keys to values. In our case, they're string keys and string values. So I listed a couple ways that you could do this. You could implement this as a linked list, which was the simple suggestion that I suggested. You could use a hash table to do this, which I think at least one student is doing. You could just use an array to do this. You could just search through the array. But either way, a dictionary requires a lookup. So given a key, you have to be able to find the value for that key. And so yeah, if you're worried about the search function, then you have to implement the search function somehow.
Yeah, no, it's just that, because when we mentioned linked list, that's like the worst one.
Yeah, it has,
Checking
yeah.
if it's in there in the first place.
Yeah, searching a linked list is, big O of N. It's bad, but I mean, yeah, but it's correct. So, optimize later, optimize once you have correctness. Premature optimization is root of all evil. So, do what kind of makes sense to you. Okay, any other questions about variables, implementing variables? All right, so from last time, so somebody asked, could we just forget about the symbol table and stack allocation and just use LLVM to do this? And as another classmate pointed out, this wouldn't really work the way you'd expect because LLVM doesn't allow multiple declarations of the same variable. So if you've got an example like this, where neither examples here, but basically if you're assigning x twice, then the LLVM will not accept that because it's static single assignment form, which means you can only assign variables once. So you could still do it, but you'd have to basically convert it to static single assignment form, which I think is probably harder to do than using stack allocated variables. So just to give a little context for this, let me get the slides from last time. Last time, what I proposed that you do for variables is when you see a new variable declaration, like int x, you emit an allocation instruction in LLVM, which is stack allocation, which says push this next element onto the stack. And then whenever you see usages of that, like say an assignment to x, you translate that to a store in LLVM. And the symbol table keeps track of the fact that T1 holds the address of that stack allocation. Now this is what real world front ends that use LLVM do. They use stack allocation for variables. And I suspect part of the reason is that it's easier to do that than it is to try to rewrite the program to have only a single assignment for each variable. So imagine if you had, maybe I can give you an example here. So imagine we had this program. Let's see, let's do x equals 1 if y equals 1, let's see, if y is greater than 10, then x equals x plus 1. This is my bad pseudocode, but else x equals x minus 1, and then print x. So imagine we have a program like this. So what's going to happen if we try to translate this to LLVM, where we, do our assignment? This is actually not even valid LLVM already. But then, we'll see later on how we implement branching, but there's going to be a branch instruction. And if you try to do something like this, LLVM is going to complain to you if you try to do this statement, because you're reassigning the variable, which LLVM does not allow. So can anybody think how you can get around this issue? How we can rewrite this so that only,
we would use the LLVM load command to put present x's value into another variable.
Well, yeah, that's basically what stack allocation is. It's offloading. If you think in LLVM, if you think of these variables as registers, in like, what did you take, CDA or computer organization logic? You learned about registers. There's a limited number of registers, and when you run out of registers, you have to use memory to back your storage. So you have arbitrarily large memory. And that's exactly what the Aloka statement is. But you're just doing it ahead of time. You're saying, anytime I have a variable, I'm just going to associate that with memory and not even worry about the registers. So we'll see a little bit of this near the end of the semester, but that can lead for poor performance in your code. You can do much, much better if you only do register operations. But there's a finite number of registers. So there are actually algorithms in the compiler world that will optimize this allocation of registers to variables. So you use the most number of variables and the least number of stores and loads to memory. That's called spilling. Spilling registers to memory is the compiler term for that. And so there are algorithms to do this. And the first step in a lot of these algorithms is to turn code that looks like this, where you have multiple assignments of the same variable, into code that looks like LLVM, where you only have a single assignment of each variable. And so there's a famous paper from a few decades ago showing how to do this transformation. But we'll talk a little bit more about how to do these analyses in order to get there. So you certainly could rewrite the code in order to have a single assignment per variable. But I think it'll be a lot easier at this step to just assume that every variable has a stack allocation, and you store and load whenever you read or write, or write or read that variable. Okay, questions on this? Any other questions? So that was a good question last time, can we just use LLVM? And I did, and LLVM does handle functions for you, so it'll actually store all of the function locals onto the stack for you. That is handled for you. You don't have to do that in assembly. But yeah, because of this variable assignments, I really strongly recommend just using the stores and loads. All right, anything else on variables? All good? Everybody's ready for project 2? Okay. And also just another kind of minor point. Rather than thinking of these as separate projects, separate .c files and separate programs, think of it as one long program for the semester that you're incrementally improving. So there's no need to make individual project1.c files. You can just have one compiler. And if you ever want to recover that old version, that's what version control is for. You've tagged it already, so you can always recover that C file. So there's no need to have multiple C files and delete them and add them. Just edit the same compiler. And your version history keeps a record of everything you've changed and committed. That's the beauty of version control. Okay. Okay, so let's get started on today's lecture. Today's lecture is on types and type systems. All right, so the question is, why bother using types? So I've given one answer up here, but I'd like to have some opinions from you. I mean, how do you feel about if you've programmed in like Python, which has kind of dynamic typing, or you've programmed in assembly, or you've programmed in C? What do you prefer? Do you like C's kind of where you get a compile time error if you don't declare your types. Do you prefer Python? What do you guys think? Let's get some opinions. Yeah.
It helps you keep track of your precision.
Yeah.
Because floats and doubles, which have different registers.
Yeah. Oh, well, that's a really good point. So it helps you keep track of the fact that actually floats and integers have different representations in the machine. So if you didn't have those types, you may accidentally try to add the representation of a floating point with the representation of an integer, and you get something meaningless. Yeah.
I prefer a Haskell system where you can define what sorts of operations or types of.
Okay, so we have a Haskell aficionado here. So if you take programming languages with Dr. Levins, you'll go all into Haskell. So Haskell has like type system on steroids. It allows you to do a lot more flexible stuff with type systems. So beyond just is this an integer or a floating point, you can characterize the methods that you can call, and you can characterize functions. I mean, you have function types in C as well, but they're a little bit more they're a little bit weaker. Okay, so no proponents of like JavaScript or writing an assembly or Python. That's interesting. I think UCF has trained you well as system engineers. Well, so Python and JavaScript do still have type systems. The difference is that C's type system is at compile time. The compiler has to check whether the program is well typed before it'll even generate code for you. And as one of your classmates pointed out, because there are different machine representations for, say, floating point and integers, it's actually really necessary for the compiler to do this if it wants to generate the actual machine instructions at compile time. Otherwise, it has to account for the fact that a variable could be any type during runtime. Yeah.
So does Python? I don't use Python a lot.
Yeah.
When you have an error, does it not do it? Like,
I will show an example in a few slides. I'll show an example of this. That's a good question. Okay, so the kind of theory behind why you use the type system is that it prevents errors during runtime. So what is a type? So a type, in the kind of theoretical world, it's a set of values and the operations on those types. That's really all the type is. So if you have an integer, it's the set of all integers, maybe from min integer to max integer if it's unsigned, maybe from 0 to max integer or to infinity, depending on what programming language you're using. And just the arithmetic operations, anything you can do on integers. So for Boolean, what are the values for Boolean? Well, you only have two values, true or false. And what are the operations? They're the logical connectives, and, or, and not, and maybe XOR. So typed languages restrict a variable's range of possible values. So an integer in C, you cannot assign a floating point to an integer in C. As we'll see in an example, the C compiler will do some trickery under the hood for you to allow you to express that, but you won't be able to actually represent floating point values with an integer type. And typed languages include Python, C, and Java. So Python, even though Python has runtime type checking, which we'll see in a bit, it's still typed language. It still enforces these types. Untyped languages like Lisp or programming in assembly you can do whatever you want. It doesn't restrict at all how you use values. They do not restrict the range of these values. So safe versus unsafe. We can categorize the kinds of runtime errors you get into two kinds, trapped and untrapped. So I'm sure you're all very familiar with trapped errors. These are the kinds of errors that the processor, if you're programming in C at the machine level, the processor will actually stop and give you the error. This is why you get a seg fault. You get a seg fault because you wrote some code that's trying to access some memory that the operating system does not allow you to access. And so what happens? The processor throws this exception, the operating system catches it, terminates your program, and sends you a signal that says you got a seg fault. So those are trapped errors, things that are caught by the hardware or by whatever virtual machine you're running on. Untrapped errors are a little bit more devious. So these are examples of this is, say you declare an array in C of size 10 and you start writing past 10. You start writing to 20 or 30. So languages that are safe they try to prevent untrapped errors, and maybe some trapped errors as well. And the difference between static and dynamic checking, to go back to one of your classmates' questions, what's the difference between Python and C's type system? C and Java and other static type check systems, they do their type checking at compile time. Although with Java there is also a little runtime type checking as well. Whereas Python, this type checking happens at runtime. So in Python, if you have a program that has a type error, it will run, it'll start running, and it won't crash until you, or won't throw an error until you actually encounter a type error. And so people in programming languages like to characterize type systems into weak versus strong. So if we take the set of all errors that we don't want to allow in our running program, and say the forbidden errors are all the untrapped ones, all the kind of devious errors that you can have in your program, but the program won't immediately stop because the processor won't catch them. We call those the forbidden errors. And a program that has good behavior means the program never has any of these forbidden errors, as defined by your type system. So a language that is strongly checked will reject any program that it has forbidden errors. It will only allow programs that have this good behavior, whereas weakly checked languages like C will allow programs that violate the type system. And so, there's all kinds of debates around, you should always use Java, it's always safe, you should never use C, you should always use C, C allows you to feel the bits. However you see it, some languages are strongly checked, some languages are weakly checked. They actually allow, so C famously allows lots of these untrapped errors to go through. So here's just a little table of typed languages and untyped languages versus safe languages and unsafe, just to kind of show the distinction here. So Java is both typed and it's safe. So it has a type system and it restricts the uses of variables, but it's also safe because it doesn't allow any unsafe programs, except for a tiny little bug in its type system that was corrected several years ago, but it's intended to be completely safe. Lisp is an example of a language. Has anyone actually programmed in Lisp or Scheme? Yeah, Lisp, lots of insignificant parentheses. So Lisp is a language that, while it doesn't have any type restrictions, it's still safe. See the language, you'll see why this is, because it has a very restricted kinds of data. So see it as an example of a language that is typed, but it's unsafe because it still allows programs that have untrapped errors, like buffer overflows, array out of bounds errors. It allows these. An assembler is a case of a language that has no type system and is just unsafe. It doesn't actually, it can't do any type checking because it doesn't have a type system. So if you're interested in kind of the theoretical side of these type systems, I recommend this paper by Cardelli. He's a famous guy in the programming languages world. And he goes all into detail about these definitions of type systems. Okay, so let's take a look at Python versus C's type system. Okay, so let's take a look at Python first. Let's see, where am I here? Okay, so I've got this Python program here. And you don't really have to know Python to basically understand what this program is doing. So it just prints out some string to show us that we're actually running and not just compiling. It assigns x to degrees. And then it adds 1.7, which is a floating point number, to some string, and sets that into x. Then it sets y to some computation, and prints y. Okay, so some votes. What do you think is going to happen here? Is this program going to compile? Is this program going to run? What's going to happen when is it going to successfully run? What's my output going to be? Yeah.
I'm going to guess that it's going to run. let's see here. So y is 1.7 times 2, so it's going to print to whatever that result would be.
Okay.
But the degrees itself isn't set with any sort of print thing, so I don't think that's going to show up at all.
Okay, so let's see what happens. Let's just try running this program and see what happens. Okay, so we get the started running output. So it did pass compilation. I mean, it's sort of weird to talk about a language like Python as being compiled, but technically it is being compiled to some intermediate language. So it's actually starting to run. But then we get this type error, unsupported operand type for plus, float, and string. So even though this program started running, Python is keeping track of the value, the types of each of these, and it's using that to try to pick which operation to use for plus. So here it's saying, I see plus in between two operands, and those two operands have two different types. I have no function that will compute that. So then it throws a type error. So to walk through this kind of step by step, I'll just like run each piece of this. So this is just Python's interactive mode. I can run one line at a time. So if I set x to degrees and ask Python what the type of this is, even though we didn't actually declare x to be any particular type, Python will tell us that x is a string. So the way these dynamic languages work is rather than tying the type to the variable name, like in our programming language or in C, it ties it to the data itself. So you can think of the type being following the data in the program. Okay, so let's look at this next line where we add a string and an integer, and as you can imagine, this is what threw the error. Because remember, what is a type? A type is a set of values, so like floating point values, and a set of operations on those values. And what the type checker does is it guarantees that whenever you have an operation, that the types of its operands match that operation. If we were to do this in assembly, for instance, or actually in C for that matter, which I'll show, the compiler would allow this, and the program would run, and it would just run not even worrying about that error. You'd get some sort of undefined behavior as your output. But here's an interesting case. What about 1.7 times 2? Okay, will this run?
Yes.
Are they the same type?
No.
No, okay. Let's see, will it tell me the type? So in Python, the symbol 2 has type int, and the symbol 1.7 is float. So these also don't match the type. Why does this work then? Or why do you think it will work?
Because you can convert it an int to a float.
Because you can convert, I could convert this to an int, right? I could do that explicitly.
I was talking the other way around.
Yeah, it should.
Sure. But if I let Python do it, it will just kind of work, right? Even though it's an integer. So behind the scenes, Python and C does this as well. It's actually, without telling you, it's changing the type of that. It's doing a type conversion on that value. So this may seem convenient as a programmer, but this can actually cause some challenges there's actually some famous bugs related to problems with types. Yeah, question?
Yeah. So are there cases where you wouldn't know if it was a float or an int?
You as who? You as the programmer, or you, or as the software?
So like with the untyped language, like saying.
Oh, with an untyped language,
Are
yeah.
there cases where like, it could be a float where you think it's an int?
Yeah. So if you have a language that is either untyped or weakly typed and allows unsaved programs. So for instance, in C, I'll show an example where you can actually. So did you guys learn about the floating? You learned about floating point representation, right? Like IEEE floating point representation. You have like mantissa and blah, 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 blah. So that representation is not the same as an integer, right? So if I had a 1 in floating point and I added it to a 1 in 2's complement, I would not get 2 in either of them, right? I don't think. I wouldn't get a 2 in either integer and floating point. So that in assembly, you can certainly do that if you want. You can just add those two representations together. And the machine doesn't care because the machine just says, I have bits, I call this instruction, I'm just going to do that operation. So yeah, if you're writing an assembly and you're not careful about your representation, then you can certainly make this kind of mistake.
What
And as we'll, what's that?
Would it come out as garbage if we're talking assembly?
Yeah, it would come out whatever operation you choose. So in assembly, and yeah, I'll show an example of this as well later. In assembly, you have, or at the machine code level, at least in Intel, you have different instructions for integer add and floating point add. They're actually different machine instructions, different like low-level hardware does those two things, more or less, at least at the ISA level. There are different instructions that do it. So you would get, if you took one in integer representation and turned it into a floating point, that might represent something in floating point. I actually don't know, but that might represent something in floating point, and that's what you'd be adding. Okay, so to kind of see why this is a little bit of, to kind of reveal this same point that there are different operations here for floating point and integer arithmetic. Take a look at this program here, and let's take some guesses as to what will be output when we run this. So I've got 1 over 10 plus 2 over 10. I add those together, then I multiply by 10. Yes. Oh, yeah. Go ahead. 3. Okay. So who says 3? Okay. Who says not 3? Okay. What do you think it would represent?
I'm not sure, but
I'm sort of making it. I'm sort of hinting at something, right? Yeah. How about you?
I don't think it's an output 3, but 3.0.
3.0. Okay. That's a good. So who says 3.0? Who says 3.0? Okay. Okay, so I have like 3 people who are responding. Who doesn't know? Who's just sort of hedging? Okay. All right, let's take a look. Let's see what's going to... Oh, do you have an answer?
I was just want to say that the thing you're talking about in the CDA is that with the floats, for some reason there's always like at least this random 1 way down the line. So I don't know if it's gonna shrink to like 3.0 or something, but I feel like if it was to write all that out, there'd probably be just like this stray 0.0000001 or something.
Oh yeah, that's pretty good. So this is exactly what we get. We get 3 points, blah, 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 0.00004 at the end. Why? Well, because I sort of constructed this example to kind of trick it into being imprecise about representing 1 over 10. So remember, this is like a kind of a finite representation of floating point. We don't have like infinite precision. So somehow, I managed to get it to, be imprecise about this floating point precision. So in this case, I don't exactly know why. I didn't go through the machine instructions that go why. But in general, floating point, the precision depends on, where. So if you have like 1 times 10 to the 300 versus like 1 times 10 to the 1, the precision of that is going to be different. I mean, in like scientific notation precision.
How would you fix it to not do that?
Oh, to not do it? Yeah, I don't know. How would I do it? I would just like solve for it. It's going to be just 1 plus 2, I guess. That's like, that's cheating? Well, some compilers can do this actually. Compilers can do this. Compilers can simplify constants. Okay, anyway, so that's just a little like sort of fun example to show the difference between floating point arithmetic and integer arithmetic. And just so you know that when if you're combining integers and floating point numbers, that you may end up with something you don't expect. So if you have a for loop that's checking that I is equal to 3, and you're doing some floating point numbers, you may have an infinite loop, because it'll never reach 3, for instance. So with floating point, you want to have a delta instead of an exact number. Okay, so that's Python's type system. So let's take a look at a C program. Okay, so I've got a couple of things going on here. I've got a double here with an explicit cast from 2 to some double, and multiplying it by 1.7 times that number and assigning it to an integer. All right, so in Python we saw that this program will run this operation on, this operation is on 2 different types actually, because this is a float versus a double. In Python, it just did the type coercion for us. So what about in C? Is this even going to run? So let's remove this.
No.
Let's remove this for a second.
Oh,
while we do this. Sorry. So let me remove the second part of this. So we'll compile first of all.
Yes, but was
We'll compile. Okay. Yes, it'll come. Let's see if it compiles. So okay, it compiles. I didn't get any warnings. Probably if I force it to turn on all warnings, it'll tell me. Oh, actually, it tells me it's an unused variable. It doesn't even care about the types. And let's print it out as well. So here's the print statement for y. All right, so we got 3. It worked. It did this coercion behind the scenes for us. And if we open the hood a little bit and look at the assembly version of this, so I'm just going to turn off optimization. And so this is how you compile it to assembly code. You can actually see that this multiplication here is, if we Google this, you'll see that this is floating point arithmetic that's happening here. So it's actually, doing this, it's casting it to double precision floating point, even though 1.7 was just floating point. And it's doing it. And then there's this very long instruction name here, which is doing the truncation to integer. So there's even a special, in an Intel at least, there's a special instruction for doing that. So that, even though at the source code level, it just looks like we're just adding numbers together and sort of not worrying about what their types are, the compiler actually has to worry about the types because there are different instructions at the machine level for doing arithmetic. And so C is very convenient because it sort of makes that invisible to you. If you program in a language like Ada or even Haskell, although I think Haskell has some ways to make this a little nicer, but if you program in a very strongly typed language that doesn't do this kind of type conversion for you, you'll just get a compiler error. It'll say, I can't add floating point and integer. It won't allow you to do that. So Ada was a language from a couple decades ago that was intended for missile control systems and things like this, where you wanted to have very safe code. Okay, so let's look at this next example, where we've got a string, which in C is a pointer to a character, and I have it set to hello world, and then I add that string to y2. So in Python, what happened in Python when I tried to do a string plus?
It said no.
It said no. You got a type error at runtime.
Yeah, this is.
So what about this program? Who says it'll compile? Okay, one person. Two people? So who thinks it'll run if it compiles? Well, actually, that's a set of 2 people. So you think it won't compile, but it will run if it compiles. That's a good way to hedge. All right, so who says it won't compile? Who says it won't compile? Okay, interesting. Let's see what happens. Oops. And, oh, whoops. So that's not the right error. That's because not the error I was looking at. Not the error I was looking at. Okay. So it compiles with a warning.
Yeah.
Gave me a warning. But it compiled. It let me do it. So why? Why did it let me do this? Yeah.
Is it because characters have integer values associated with them?
Well, so this is actually, so look at the type of this. What is the type of temp2? Is it a character type?
It's
A character array, which is a string.
It's a pointer to a character. If you remember, they taught this in CS1, right? Arrays.
Arithmetic, that's what that is.
Right, exactly. It's pointer arithmetic. So this temp2 is not a character. It's not a string because C does not have a string data type. It's a pointer to a character, or a character array. And so its value is what? What is a pointer? The value of a pointer? Yeah. What's that?
a memory address.
Well, yeah. I mean, I don't know. Well, I think it depends on the word size of your machine, or it depends on some machine-specific behavior. But yeah, exactly as Gleisman said, it's a memory address. It's a memory address. That's what a pointer value is in C. So you can actually print it out as you can print it out. That's the actual memory location in virtual memory. Yeah.
So if you were to do y2 equals 1 plus
Oh, and dereference it. Oh yeah, okay. So someone asked, what would happen if I dereference temp2? First of all, yeah, okay. Yeah.
Would it add like the integer value of h?
Yeah, exactly, good. It would add the integer value, the ASCII value of h. Because what happens when I do a dereference? It takes that memory location and it just follows the link to that. It dereferences that memory location and gets whatever value you have at that memory location. And because C knows that this is a character pointer, it'll know to only look at 8 bits at that memory location. So C is like weakly checked, it is doing a lot of type checking to help you out. So it knows that this is a character pointer rather than, a pointer to a double precision float, which would be, whatever, 64 bits or whatever it is on this machine. And will only give you the 8 bits at that memory location. And that 8 bits corresponds to the ASCII code of H, because offset of 0 from a memory location that represents an array is the first element of that array. That's why you have, that's why you have base 0 indexing in C and other languages. Okay, good. So let's not dereference it. Let's go back to the example where we just have the memory address. So now we know, so knowing that, who thinks this is going to compile? Okay, a few more people think it's going to compile. It did I show it compile? Oh, okay. So who thinks it'll run? Who thinks it'll run without an error or without a trapped error? Okay. So let's run it. Did I make any changes? Okay, and it ran.
Yep.
It ran, and what did I get in binary? I got what was likely the memory address of temp2, this array,
It's
plus
not
1.
divisible by 4, so it added 1 to that memory.
It added 1 to it. That's right. What's that? Say it again?
The warning.
Oh, what was the warning? It's warning you that you're doing,
Oh, point of
yeah, you're making it you're turning it into an integer from a pointer without explicitly casting it. So the C allows you to do pointer arithmetic, but modern compilers will try to warn you of this because it's kind of a dangerous thing to do. You can access this is basically like allows you to do untrapped errors. So you could read past the end of an array. I could read past the end of hello world and start really breaking stuff. Like for instance, if let me see if I can break something here. So if I want to print the character at temp2 versus the character at temp2 plus 30. So as we, I have to dereference. So I'm trying to print the character, not the string. So I think I have to dereference it. Let's see what happens. So I get H and I get nothing.
Well, it went way off the edge of the screen. Who knows?
It may be empty. Oops. Oh, it's a 0. So I entered some space that was 0 allocated. I could also look before it. Could do negative 30. See what's before it.
Ooh, that's dangerous.
Okay, just some random value in memory, probably something on the stack. And we'll see. I'll have a demonstration later when we talk a little about security, about how you can use the blow up, mess with the stack in order to do some security violations. Okay, so that's sort of like a little quick overview of these distinctions in the type systems between Python and C. Python is strongly checked, but it's runtime checking. C is weakly checked. It's not strongly checked, and it's all at compile time. And in fact, part of the motivation for allowing weakly checked is to make the compilation easier. At least I suspect. Okay, questions on this? Though? Yeah.
So what's the advantage to runtime type checking?
The advantage to runtime type checking.
Yeah, because it seems like you're subject to a lot of errors.
Yeah, so the advantage to runtime type checking is that there are certain properties that are very hard to check at compile time or impossible to check at compile time. So Java, for instance, has you can kind of think of it as a hybrid type system where it's mostly static checking, but it does allow for runtime checking as well. So there are certain properties, so for instance, not allowing out of bounds errors. Right now now I have a fixed length array, But if I have a variable size array and I'm computing the index into that array, if I'm doing some complex computation of the index into the array, say I'm reading from input and trying to compute the index on an array, it's very hard to prove at compile time that I won't have an out of bounds error. So what Java does is the array has the length bound with it in memory. So the array is not like a C array, it's an array, it's like a C array, but it has an extra length field. That's why in Java, if you've ever had an array out of bounds error, that doesn't happen at compile time, right? That happens at runtime. Yeah, so properties like that are much easier to check at runtime. Was there a question? Yeah.
Is that why, in C, you can't have variables in an array, the links, standing into the links of static arrays?
Yeah, this is a good question. Can you have arrays that are variable in size?
Well, I'm thinking of declaring.
So if I declare an array like this, but instead I declare it of size y too.
Yeah.
So I thought this was also prohibited as well. So there are two things that are going on here. The compiler can try to figure out that there's only one possible value for this. It's called constant propagation. So if it's only computations using constant values, then it'll try to figure out what that is. But GCC apparently has a way to allow you to have runtime allocation of arrays on the stack. I actually wasn't aware of this. There's some special library functions that you can do. You can Google this, but Google GCC variable length arrays on the stack. And there is, so GCC allows these variable length arrays. And there is a special call that it does. So I can't remember where it is. So anyway, they do some, there's documentation for this. But anyway, you can kind of go down this rabbit hole if you want to take a look at how it works. I don't actually remember how this works, but the compiler will insert some instruction that will do the allocation on the stack at runtime and manage it for you. Okay, anyway, a bit of a rabbit hole for me, but yeah, so it does work, but I guess it's kind of a GCC extension maybe. I don't know if it's part of the C standard or not. Okay, other questions on these examples so far? All good, okay. So these examples are in the syllabus. You can take a look yourself. They're under the lectures. They're under the lectures under lecture 12. There's a directory there which has all of these examples, and you can play with them. Oh, actually, there is one more example I'd like to show. This one's a little bit more involved. Let me try to run through it quickly. So printout started running to prove that the program is running and not just compiling. I assign a floating point value. I assign that to an integer and print out that integer. So what do you think is going to be print out when so first of all, is this program going to compile, do you think?
You might get a warning, but
Might get a warning, but will it compile? Yes, it'll compile. It'll compile. So what about this first print statement? What do you think will be print out, this first print statement? Uno, one, right. All right, let's look at this next set of instructions. I now take, so pointers. So I take a pointer to X. So now I get, basically just think of it as the memory address that this value X lives in. It's some address on the stack. P is now the memory address that lives in. And I do this little trick here to just copy that exact address. So the address is being copied from P. Now IP is just the exact same address, right? This is just assignment. And then I print out that the value at that memory location. So I'm dereferencing IP. I'm dereferencing it. And I'm printing out that dereferenced value. But I'm doing a little trick. I'm dereferencing it, telling C that this is a pointer to an integer. So remember, the original pointer was a pointer to a float. Is this too much pointer stuff going on in your head? So all of these, this P and IP and this, all three of these are pointing, there's the same memory location. This is just a little bit of a trick to cast this floating point pointer into an integer pointer. So in the first print statement, just one is going to be print out. But what about the second one? I effectively do something kind of similar, right? I'm trying to cast it from floating point into integer. So what do you think is going to be print out in printf? Who says 1? Who says 1? Okay. Who says not 1? Okay, it's about 50-50 of the respondents, of the people who responded. So let's take a look. No warnings. Although if I do W all, it probably, doesn't even care. All right, so I get 1 for the first one, of course. For the second one, I get some random integer. So for those of you who said it wasn't going to be 1, why is this happening? Yeah.
Because the floating point has a mantissa and an extra and it's just parsing that section of memory like it was an integer.
Yeah, exactly. So this is the floating point representation of 1.7, but now it's being interpreted as an integer, and it's being printed out as if that were an integer, as if that data were an integer. And so this typecasting is allowed in C. You can always use a void pointer, which means like C does not know or care what its type is. And you can always do that. That's how I was able to get around C's type system. So this is why C is weakly typed, because then I can actually do this at runtime and at compile time. It'll actually allow me to do this. Whereas Python, it'll compile, so to speak, but it won't run. It'll keep track of the type of the value that's at P. C only knows what type it is according to the symbol table. Yeah?
So because IP is a void pointer, you can cast it whatever you want.
Yeah, C just allows you to cast whatever you want, which I actually didn't realize till last semester when I constructed this. It just allows you to do it. So if I were to try to cast it immediately to an integer pointer, C, it actually would prevent me from doing this. So I can just show that real quick. If I were to try to cast this to an integer pointer, I think C will complain if I do this. The C compiler will complain. Oh, never mind. It doesn't complain. Okay, anyway.
Oh, it's the same thing.
Oh, I guess it doesn't complain. Okay. I thought it did for some
I
reason.
thought it would.
But, okay.
I think C++ will complain.
C++ will complain? Okay. So, yeah, I thought it would, but oh well. Anyway, okay, so questions on this? Any more questions? So you can see all these examples in here. You can sort of play around with type systems. Okay. So that's Python versus C. Okay. So let's look at the actual algorithm for doing static type checking. Your project 2 will do kind of a very simple version of type checking. But I'll show you, in our language, I've only given you so far a single type. We only have integer. We'll only ever have one primitive type, only one integer. There'll be no bool, no floating point. But I'm going to run through some examples of languages where you have multiple types and what this type checking algorithm looks like. So the way static type checking works, at least in C-like languages, is as you process the program, you process the tree representation of the program, and you basically do this post-order traversal. When you see variables being declared, you store them, the strings of the identifiers and the actual type in the symbol table. And then as you go through the arithmetic operations or assignments and function calls, you check to make sure exactly the property that we want, that any operation is using the correct types. So if we've got multiplication, we're using 2 integers. If we've got floating point multiplication, we're using 2 floating points. And when you have x in an expression, you don't know what its type is unless you look it up in the symbol table. So the symbol table is like this global state that you keep track of while you're compiling your program. So that's how you know. So you look up in the symbol table in order to tell you the types of variables. But constants are easy. Constants just have a predefined type. according to your language. So at least in our language and in other languages like C, 3 is defined to be an integer, no matter what. 5.2 is defined to be a float, no matter what. C doesn't have Boolean, but in languages that have Boolean, true is defined to be a Boolean type. So questions on this at all? So in order to talk about types, I'm going to give a little kind of syntax that's sort of popular in the programming languages world. So scalar values that are not arrays, that are not functions, that only have a single value associated with them, they're called primitive types. So this is int, char, long. They only have a single value. They're called primitive types. And so the kind of fancy programming language is a way to write that. And for the Haskell programmer in the room, you'll recognize this, this is Haskell syntax, right, as well? Or at least ML syntax. X has type int. So X is the symbol, int is its type. You'll see some programming languages actually use this kind of syntax. Now, what about for functions? How do we describe these operations on different values? So if f takes two integers and returns a Boolean, we can describe this type like this. We have the symbol f, which is the name of our function, and we use a tuple of values, just like in math. So here we've got two values that it takes, and they both have type int. And this little arrow is conventionally used to mean function. So this means a function that takes a tuple of two integers and returns a Boolean. Questions on this notation at all? Pretty straightforward, right? This is a very common notation in computer science. You just have to kind of like remember it. So the question is, okay, so a little test. Here's my type for f. What is the type of multiplication, the multiplication operation? And I just realized this actually might be a little bit of a trick question, but I didn't intend it to be. So what's the type, using this kind of notation, what's the type of multiplication? Any takers? Yeah.
It could be multiple types.
Yeah, it could have multiple types. So we won't talk as this is like, you can have sort of operator overloading, or what's it called? What's that called? Like polymorphism, I think it's called, overloading polymorphism. You can have that, but let's just pick one. Just pick one. Float. Okay, so what would the type of float be? I mean, what would the type of multiplication for float be? What would its type look like, using this pattern of notation?
Like as if like so it'd be like function, colon, float. Actually, I don't know.
Well, so that's for a scalar value. That's an x. That's if f was a float value. Yeah. Yeah, good. It would be float, comma, float, arrow, float. Because what does floating point multiplication do? It takes two operands, both of type float, and returns a float value. Make sense? So I put the one for integer here, but if we have integer multiplication, oh, whoops, that's totally wrong. Never mind. It's supposed to return an int. I did some bad copy-paste error. So anyway. So yeah, if you had, so in the cases where you've got the same symbol but it has multiple different types, I think that's like polymorphism. Take programming languages. Dr. Levins will talk to you all about that. Okay, so just a little refresher of symbol tables. The symbol table just keeps track of the variable name, the type, and the address for use in compilation. So the compiler assigns memory to each variable, maintains a mapping between names and locations. Whenever there's a new declaration of a variable, it creates a new mapping in the symbol table. And when these variables are being used, either stored or loaded, it refers to this symbol table just to check to make sure the variable is used in the appropriate way. Okay, so let's do a little demo of what this type checking will look like on each of these programs. So this is effectively the algorithm you'll be writing when you start emitting code for these programs. All right. So where's my Okay, so let's see, what was this? I have here. Okay, so my program was, I'll just write a kind of quick and dirty parse tree for this program. So it was int x followed by int y, followed by read x, followed by, well, let's start drawing the parse tree. So I'm just, to avoid having to draw the entire parse tree, I'm just going to do it like so, where these are all declarations. This is a statement, read x is a statement. And then I've got another statement over here, which is my assignment of y. So I've got y equals an expression. I'm going to sort of elide some of the details of this tree, like some of the epsilon nodes. But just to get the idea, we've got, correct me if you notice an error, please. Here's x. Okay, questions? Is this all good? Does this kind of make sense? This is what your parse tree should more or less look like. I mean, if you were to make a parse tree of this, you can also just think of this as the set of recursive calls that your parser goes through. So your parser starts at program. It tries to match declarations, and then when it tries to match a declaration, it matches int followed by an identifier followed by a semicolon. You have a loop, declaration star, so it reads both of these declarations. Then it starts reading statements. It's these that you have a read followed by an identifier followed by a semicolon. You're done reading that statement. You recursively read a new statement. You see that it's an assignment statement. So you have y followed by equals, and then our entire, expression parse tree that we went over a couple times. So questions on this, or any mistakes that you see? All good? Okay. So to do our type checking, we also need our symbol table. So let's call this ident and type. Okay, so the way the algorithm works, the type checking algorithm works, is you just traverse your tree in post order. And whenever you see, say, a declaration, you insert that new symbol x into our symbol table and record its type. So for your project 2, you can actually assume everything is an int, but I'm just going to kind of go over this to show you what this type checking algorithm looks like. Yeah?
So do we need to store the memory address of,
Yeah. You do also need to store the memory address. So if we were generating code, so I'll go over this a little more next time, generating code. But if you're generating code, yeah, your symbol table needs to also have the memory address. For sure. But I just want to show the type checking algorithm part of this. And then we'll bring it together a little more next time with the code generation, type checking, and everything. So yes, you definitely need to be storing the memory location. Okay, so we finished reading this declaration. Now we're reading the next declaration. We see that we have a y also declared as type int. And then we see this read statement in the middle. So what do? We see that there's an x being used. So when you generate code, you're going to have to do a load from the memory address that you stored in the symbol table. But you also just need to make sure that it's actually a valid symbol, a symbol that's been declared before. So you do a lookup in your symbol table and you see, okay, x is there. So this statement type checks. Make sense? So you can kind of think of the read operation as being a type that goes from a single integer to maybe void, You can call it void. So we can think of it as a special function whose type takes one integer and returns a void. So if we were worried about multiple types in our language, then we would check, we would look up the type of x, we'd see that it's an int, and then we'd match that type against the type of the read function. Make sense? Make sense? Yeah.
What would happen if we didn't have X in that situation?
Well, I mean, if it was just empty?
Let's say it was like read Z.
If it were Z, then Z would not be found in the table. So you do the lookup, you do the lookup in the table, and you would say Z not found.
Okay.
And that would be a kind of type error. So maybe I should annotate the operations here. So this is lookup X. You want to look up X in your table to make sure that it exists and to make sure that it is of the appropriate type. So keep in mind for project 2, you can assume that everything's an int. So you don't have to do this full type checking yet. Once we get to project 4, we'll have to do real type checking because we have functions. Okay, so now we get to our statement. And okay, so we're doing a post-order traversal of this statement, this assignment statement. So what's the first thing we look at? What's the first child that gets looked at? The left one, the y. So what do? We look this up in the symbol table. We look up y, and it tells us that y is an int. And just like this told us that y is an int. So just like when we were computing the expression's value, or when we were generating code, this node you can think of this node as being annotated with the type. So before, when we had the parse tree, we didn't know the types of any of the nodes. We didn't know that the types of the values at those nodes. But the type checker, you can think of it conceptually as annotating each node in the tree with the appropriate type, at least for an expression tree. Okay, so we found that y is an integer. So we attach that to our tree. And now we move to the right child, e. So just like when we were trying to generate code for this and find all the local variables, we ask, okay, what is the type of e? So what we now know is that we want to know that whether e is int or not. Because if e is not int, then we can't assign it to y. So this is the same kind of recursive function that we've been doing for code generation, for tree evaluation. We have this recursive function that says, give me the type of this node. And it will just recursively go through its children to figure out what that type is. Just your classic post-order traversal. So you're going to become very, very good at trees during this class, hopefully. Okay, so in order to find out what the type of e is, we have to look at its children. So if we look at its left children and see that we've got the number 1, well, what is the type of 1? It's an int. It's always an int. So we now know that this left child is an int, and we can just propagate that information up the tree, just like we propagate it for doing code generation. Okay, so we've handled the left side of e. Now we go to the right side, we get to e prime. And e prime tells us that our operation is a plus. So we can think of the type of plus as being what? So what is the type of plus here? Let's assume, let's assume for now we've only got integers in our language, yeah.
Is it int, comma, int, arrow, int?
Yeah, exactly. So the type of a plus is built in to be int, comma, int goes to an int. That's the type of plus. Okay, so we now know the type of the operator. We know the type of the left operand. So now we need to figure out the type of the right operand. Again, we have to do this recursive type checking algorithm to say, what is the type of this t node? In order to find it out, what do? We look at the left child, and we see x. So what do? What do we do to find out the type of this left child?
Look it up.
We look it up. We look it up in the symbol table. So when we look up x in the symbol table, it tells us that the type is int. And now we can continue on to the right child. We get this multiplication. Just like addition, it has this type function type of int goes to int. And then finally, the right child is a constant, so it tells us that the type is an int. Okay. So again, just like with the code generation, this right recursion makes the tree traversal a little bit more annoying than just a pure post-order traversal. So in order to type check the multiplication, just like you passed the intermediate value to the parent t and back to t prime, now t prime has all the information to check that the usage of multiplication is correct. So it knows the type of the left operand, it knows the type of the right operand, knows the type of the operation that you're performing, and so it can just say that, okay, the two ints were used as parameters, and my return type is an int. So because these two parameters match, and the return type is int, that tells us that t prime's type is also an int. So the return type of the function is the type of the node that is describing that function. Does that make sense? So the return type of the function tells us what the parent node's type was. And so we can communicate that int to its parent and do the same thing. So now we've got a plus. We know that its right operand is an int. We know that its left operand is an int. So what is the resulting type of that plus operation? Also an int, right? We know that the resulting type is an int. And that can be passed to its parent. And so finally we have this assignment operation. And the type rule for assignment is that the left and right hand sides should be the same type. So that's how we prevent, if we had a floating point representation, that's how we make sure that we don't accidentally make the floating point representation set to a memory location that is meant for integer. Make sense? Questions on this process so far? Yeah.
If we weren't using just ints, would we be able to say, like, okay, so we have a plus and we're able to match those, and then we just have like a bunch of ors about like, which
Oh, if they're,
return to the parent then? Since
you mean if there are multiple plus instructions?
No, more like if we had multiple ints and then floats. And
Well, if you had float, so remember that plus can either be integer arithmetic or floating point arithmetic. At least we don't have a machine instruction in the Intel ISA that will add integers to floating points. Whoops, we only have integer arithmetic or floating point arithmetic, but not both. So if we wanted to kind of overload this symbol to have it kind of dynamically pick which operation to use based on this type checking process, we could do what you're saying. We could match the two operands to either int or float, and use that to kind of disambiguate this polymorphic addition. Yeah, sure.
Okay, so we go through this process, and what if we go through this tree and there's a character instead, and it's like the operands don't match? Do we emit the error then?
That's a good question. So that depends on your language design. So it depends on what you want in your language. So certain languages like Ada will just say type error. If I don't see the exact types I want for this operation, then I won't allow this to compile. What C will do is it will coerce these types. It will insert the type conversion for you. So just to do kind of a little example of this, if I had a plus expression in C like this, and let's say this x is an int and 1.7 is a float, then during code generation, so I think, so most of you have already done code generation for this plus here. You know the left and right temporary variables, so you just emit an add instruction. If you wanted to do this type coercion that C has, there's some temporary value here, T1, that gets passed back, and 1.7 gets passed back here. This is my temporary variable. Then I would actually need to emit code that first turns T1, actually emit code that converts T1 into a floating point. So there are instructions in LLVM to do this. I don't know exactly what they are, so I'll just call it float convert. And then you would do your floating point add, which how's that done in LLVM? I don't remember how the floating point add works. Is it the same instruction, or is it a different? It might just be a different type. I actually can't remember. But effectively, you'll get floating. Let's call it floating point add. You'll get floating point add between 1.7 and T2. So this is exactly what C does. So it just emits extra instructions that do this conversion for you automatically. So this is one of the kind of benefits of the type system. You know exactly where you need to do this insertion of conversion. But this is a language design choice. This is not a natural law or anything. This is just how do you want to design your language.
Okay, what if it's an error and when you could kill it before it goes any further?
If it's an error, so remember, type checking in these languages, static type checking happens at compile time.
Right.
So we just stop the compilation and say, you, the developer, have given me something that will be unsafe at runtime, and I won't even generate code for this. Yeah.
So for us, that would be like, so if we see an error, it would be like, oh, encode, just print this message and exit 0.
Yep. Yeah. Exactly. So when you see, so I don't think I have time to go through the other example in detail, but I was going to give you a case where you have a bool being added to an int. Why is this not here? So I have a bool being added to an int. There is no Boolean arithmetic. I mean, in C actually doesn't even have a Boolean type, but there's, if you think of a language that has an actual Boolean type, there's no arithmetic that combines integer and Boolean. So you would see that this is an int on the left side and a bool on the right side, and you would know that the type of your plus takes two integers to an int, and you would see that this doesn't match. So because that doesn't match, voila, you have a type error. That's all a type error is. It's just that the compiler. One way to think of a type checker is kind of like a theorem prover. Like in math, you prove theorems. The type checker is actually proving something about the input program. In order to make sure that it's using the correct types, it's actually proving that your program for all possible inputs is not having any untrapped errors. It's proving that property. And so this whole compilation algorithm, you can think of, or this whole type checking algorithm, you can think of these leaves, like here. These leaves are like axioms in your logical system. So like I can't think of, so if you're trying to prove that multiplying two even numbers results in an even number, right? This is like did everybody take math like this kind of basic math logic where you try to prove, multiplying two integers results in or multiplying two evens results in an even, multiplying two odds results in an odd. So you prove this. How do you prove this, right? You have these axioms, these assumptions about the language that even numbers are 2i, whereas odd numbers are 2i plus 1. So those are your axioms, and then you go through a series of logical steps to prove that in all possible cases, the multiplying two even numbers is even. So it's a very similar process here where the axioms are the leaves of the tree. So the known types, like the declared types here, or the known types of operations and constants, those are the axioms. And each step of this post-order traversal is a check that each operation is being applied to the right types. And so this is actually literally doing a proof that the input program has no untrapped errors, where untrapped errors is defined to be this type safety property. And so there are actually theorem proving tools, interactive theorem provers that are based on this notion that type checking is a type of mathematical proof, and you can actually have a program that will help you do math proof and automatically check that those proofs are valid. So for anyone who sort of does not like math so much, you can sort of treat math as programming and just write a program that will help you do this math proofs. Okay, anyway, so I think we're at 45. That's the end of it. So for project 2, all you really have to do is check whether the types are defined. But once we get to functions, we're going to be able to define our own operators with their own types. And then we'll have to do some type checking. That's like in a month or so. Yeah.
Are we doing error checking for our program?
Compilation time. Compilation. Yeah, compile time. So this is all. Right. So I'll show next time how to sort of merge this with code generation. You'll do both at the same time.
If we're doing that, then we prefer single file twice.
You don't have to. You actually don't have to. You can do it all at the same time.
Oh, really?
Yes.
Because I was
Yeah.
like, oh, we have to go through it one time and then we have to go back to check the whole.
You can do it that way. You can do it that way, but because you don't have,
Yeah, I'd rather see the trick.
it's going to be easier doing it all at once.